Previously, we have been studying empirical formulas. Empirical formulas are the simplest, lowest whole number ratio of elements in a compound. Now, ionics are always reported as empirical formulas. Maybe I'll even make note of that. Ionic compounds are always empirical formulas. Empirical formulas. Ionics are always reported as the simplest repeating pattern in the crystal. So for example, like way back in the day when maybe we had something like lead plus 4 oxide, oxygen minus 2. And we said, there's two ways you can write the formula. You could just balance it. And if you balance it, you'd say, okay, to make these charges neutral, I need 2 atoms of oxygen. PbO2, plus 4 minus 4, game over. Now we said the other option is this crisscross method, which is fine, but there are a few times where it doesn't work. It doesn't lead you to the right formula right away. Where if you had like Pb2O4, then we said, no, we'd want to simplify that to the lowest repeating pattern in the crystal. So then we would never leave an ionic as a 2-to-4 ratio. We would simplify that, and the ionic formula would be the 1-to-2. Ionics are always reported as empirical formulas, but covalence may or may not be the simplest whole number ratio of elements. Covalents share electrons, and they exist as individual molecules, not like a giant crystal, and sometimes you just get really big molecules. So here they're showing us a molecule of methanol, or it's also known as formaldehyde. That's a pretty small little molecule, CH2O. That's its real formula, that's the real structure of the molecule, a 1-to-1 ratio of carbon to hydrogen to oxygen. But we can often string together carbons or hydrogens or nitrogens, all these non-metals, and they can bond single bonds, double bonds, triple bonds, and sometimes they just make really big molecules. And so here we've got ethanoic acid, and its ratio is twice that of the original formula. Now we've got a C2H4O2. That's just the real formula of the molecule. It's just a bigger molecule. Glucose is really similar. It's C6H12O6. They all simplify to the same little empirical formula, but often with covalents, which are all nonmetals, you just get these bigger versions of that little empirical formula. Those are called molecular formulas. It's like the real formula of the molecule. Molecular formulas are really only going to be used then in reference to covalent compounds, so all nonmetals, which, sometimes they're just big molecules, and we really can have 6 carbons, 12 hydrogens, and 6 oxygens. The problem comes in trying to determine a molecular formula. Now, we were determining empirical formulas given percent composition data. The problem here is that these guys, if they have the same empirical formula, they're actually going to have the same percent composition. And so that percent composition data will only directly lead me to an empirical formula. I'm going to need a little bit more information in order to get from an empirical formula to a molecular formula. For example, what if we had data kind of like this table? If you know the molar mass of something like methanol, and yeah, I can look it up on a periodic table. I can add a carbon and 2 hydrogen and an oxygen and get about 30 grams per mole. How could you use that to determine the molar mass of the ethanoic acid and the glucose? Now, obviously, we know that we could just go to the periodic table and add them up. But there's another option. Check out this first set of examples. So CH, something like CH would be an empirical formula. That's the simplest ratio, a 1-to-1 ratio. Well, if you add carbon and hydrogen, you get a molar mass of about 13. Well, now look at like ethine. It's a C2H2 ratio. And they're showing that we could just double the mass of the empirical formula, since here the ratio was just doubled. So if the 1-to-1 ratio had a mass of 13 grams per mole, if the ratio doubles in the formula, we can just double the mass. Now, obviously, I could check that on my periodic table. Now, for ethine, if I add 2 carbons plus 2 hydrogens, oh yeah, I do get a mass of 26. If you have benzene and the ratio is 6-to-6, well, you could just multiply your empirical mass by 6 and get a mass of about 78. So using that pattern, what if I have a ratio of 1-to-1 methanol and the molar mass is 30 grams per mole? Well, now I see that I just doubled the ratio in ethanoic acid. Now it's 2-4-2. You guessed it. You can just double that mass. Oh, sweet. The mass should be about 60, right? 60 grams per mole. I would just take 2 times 30. If the ratio in the formula doubled, you can double the mass. I can do the same thing with glucose. The ratio looks like it was multiplied by 6. Instead of 1-to-1, it's 6-12-6. So we can take that little empirical mass and multiply by 6. So now I should be around 180, right? So that would be 6 times 30. Okay, so in order to go from an empirical formula to a molecular formula, we're going to be concerned with the ratio in the empirical formula and how that compares to the ratio in the molecular formula.